AKVIP Perspective on AADL. Architecture-Centric Virtual Integration Process, AKVIP, is a set of technologies and practices that specifically have been designed and demonstrated to provide early detection and continuous verification throughout the lifecycle. The purpose of the AKVIP is to address the affordability and associated risks of developing complex software-intensive systems through early virtual integration and analysis before implementation. A unique contribution of AKVIP and AADL to the authoritative source of truth is the ability to support continuous integration at the architecture design level, complemented with agile development techniques. The component interaction complexity is managed by requiring components to be compliant with an architecture model. Incrementally evolving architecture models are continuously analyzed along multiple functional and non-functional dimensions. Consistency of these analytical models with the evolving system design is maintained by auto-generating them from a common annotated AADL model of an embedded software system. This reduces manual replication and maintenance of information across different models while enabling analysis of cross-domain effects within this integrated architectural model. AKVIP applies across development phases, starting with requirements engineering and going through verification and qualification. Different kinds of information at different levels of detail are used in the different phases. These slides were developed with two viewpoints in mind: model creators and model users. Model creators are responsible for providing a sufficient amount of information to describe the proposed system and support further AADL analysis. Model creators will specify data processing and transmission, communication transfer mechanisms, as well as system architecture to outline how the data is handled. When the model is ready, model users can review analysis provided by AADL to check for errors and inconsistencies in current design, and to verify that the current model meets the requirements and produces sufficient results. We will use a portion of our Simple Control System, or SCS, model. The constructs presented here focus on system latency. Some features have been omitted for pedagogical purposes. The Simple Control System model consists of three main elements: sensor, controller, and brake actuator. Lines between main components represent connections that control data flow, e.g. exchange messages, remote call, or RPC. Buses provide data exchange mechanisms between components. In real-life scenarios, different vendors might need to be utilized to purchase each component. Even though vendors often list the specifications of their products and available communication methods for a purchased part, the system engineer is still responsible for putting all pieces together and making sure that components can communicate with each other. It is important to note that this is one of the areas that introduces a lot of errors, which is why using AKVIP methodology, along with AADL analysis, is so critical. It virtually integrates multiple components that you wouldn't see working together normally before implementation. AADL analysis can help identify errors in device communication that otherwise would be missed. As you can see on this slide, there's a variety of AADL analyses available right out of the box in OSATE tool. These analyses can be ran on the same model to verify that no device is overloaded and sufficient power is supplied to components. In-depth description of each analysis can also be found in the Help section of OSATE tool. Getting back into AKVIP methodology mindset, we would want to get more familiar with the cycle of changing a model and running analysis until all of the requirements are fulfilled and no issues are identified by AADL analysis. As we get later into project development, things will be more precise, but predictable analysis provides early guidance for decision-making. If any changes are introduced, Model Creator must run analysis on different types of attributes to ensure that modularity stays within acceptable bounds. With predictable analysis, we are interested in analysis of different types of attributes, not just latency, nor just safety or security, but all of those. For example, model user might look at the initial latency analysis and see that it doesn't meet the requirements. Model Creator will decide to improve latency of the particular flow and to make trade-offs. However, the analysis should be run again to verify that modularity stays within acceptable bounds, and other areas, like safety and security, are not negatively affected. Let's review our example Simple Control System in more detail, and identify the properties that contribute to latency analysis. As we've seen before, Simple Control System contains three components: sensor, controller, and brake, as defined as subcomponents in high-level SCS system implementation. There are also buses defined as system subcomponents to model a data exchange mechanism. And just down below are two connections, C1 and C2, that connect data ports between sensor, controller, and brake, and define the direction of information flow. Moving on to device implementation and properties needed for latency analysis. Simple Sensor, on the top right, has a latency property set to 3 to 5 milliseconds. Simple Controller, on the bottom right, has a latency property set to 3 to 5 milliseconds. Simple Brake has a latency property set to 3 to 5 milliseconds. AKVIP is most useful when components like sensor, controller, and actuator are made by different groups and vendors. If different parties are building components separately, there's a good chance of missing important details due to miscommunication. The potential for interaction mistakes are made a little more clear when you look at the error model and errors, like invalid types. For example, if one person is sending a message and the other one is not expecting a message, which will be covered in a later tutorial. AKVIP can also be used to compare a product from different vendors before purchasing to ensure the best fit to the proposed system. Here are the few examples where model would need to be reassessed. New component has been added to current design and need to confirm that no additional changes are required. Vendor updated a component and now specifications have changed. Choosing which vendor to purchase a component from, looking for best fit for the system. Usually, separate tools are needed for different kinds of analysis, which requires specifications in the model to be represented differently for each analysis. In AADL, system model represents authoritative measures of multiple disciplines, and all attributes are defined as properties. Plugins can be added to address some of the attributes, but the process of structuring the model and running analysis is the same. AKVIP augments existing development process by adding verification and integration steps into design and analysis steps. Running the AADL analysis before implementation begins can solidify the model up front and cut down costs in the end of the project. AKVIP methodology can also shorten the time and effort spent on the project. Even though more time is needed during the design stage due to running analysis and verifying the model, less time is spent in development and testing later on, since the majority of the issues have already been identified and fixed in the theoretical model. Overall, identifying and correcting errors early takes significantly less time than designing a solution after the whole system's testing is done. Here's an example when system model might need to be reassessed. Sensors are guided by the Sensor Open Systems Architecture Consortium that creates standards for sensor devices. For example, if you are planning to upgrade your sensors to the newest standard, you might ask yourself some of these questions. Which system components will need to be replaced? Will any other components be affected due to this upgrade? How much will the upgrade cost, or how much time is needed? AKVIP methodology will help you answer these questions. Now that the system model is specified, let's look at AADL latency analysis provided by the OSATE plugin to understand problems in current system design. The latency analysis is performed on AADL models that include end-to-end flows and calculate minimum and maximum latency, taking into account a wide range of latency contributors. It does so based on latency budgets assigned to different architectural elements, as well as based on design information as architectural designs evolve. The AADL model may range from a functional architecture with latency budgets at different levels of decomposition, to a task and communication architecture with execution rates mapped to a hardware platform supporting partitioning. The fidelity of the analysis is determined by the details in the AADL model. The topmost line of the analysis shows the settings that were selected. Min and max columns represent ranges based on certainty. If a component has a metric specified, it will be listed here. The totals will be shown on the bottom to calculate expected latency. The left-hand column of the report shows items to which latency metrics are attached. Analysis itself shows how components interact with each other, similar to integration testing, which is usually not done until vendors bring in all components or parts together for assembly. As a vendor, This analysis could help in selecting a proper part that meets system requirements without getting to know the whole system in great detail. As a system engineer, different models and parts can be added to the system to find an optimal combination that meets system requirements. AKVIP methodology can create an authoritative source of truth model, as separate groups can represent their part of the model in the same way and keep the architectural model shared, integrated, and up to date. As a model keeps growing, each discipline criteria can be verified without extensive knowledge of the entire system. AKVIP is most useful when components like sensor, controller, and actuator are made by different groups or vendors. If different parties are building components separately, there is a good chance of missing important details due to miscommunication. The potential for interaction mistakes are more evident when you look at the error model and errors like invalid types. For example, if one person is sending a message and the other one is not expecting a message. To reiterate, we'll cover this in a later tutorial. AKVIP can also be used to compare a product from different vendors before purchasing to ensure the best fit to a proposed system. All of those are available possibilities due to predictability of how properties are described in the model, and those are possibilities due to the unified process that highlights specific model areas in question. Here's an example of how to define a latency property as an authoritative source of truth in this model. And you have to remember, as a model evolves and becomes more complex, having authoritative source of truth properties avoids confusion because all of the small details are specified in the model. Here's an example of device specification. We're looking at the brake device. As you can see, we have a flow that specifies the direction of data exchange. Brake flow is marked as a flow sink, which means it will receive data from another component through the data in data port. Here's an example of the bus that allows data exchange between components to happen. It is important to note that if you want components to talk to each other, they should be connected to the same bus. This code snippet shows how bus model can be defined in AADL. Bus 1553 has 3 properties with data size set to 8 bytes, bandwidth budget set to 512 kilobytes per second, and bandwidth capacity set to 768 kilobytes per second. In conclusion, AKVIP perspective can be successfully applied to the AADL model at any stage of product development and validate the proposed design before implementation has started. By running analysis, the user can intervene earlier and identify system components that contribute to system issues. It is important to remember that the fidelity of the analysis is determined by the details in the AADL model.